Okay, so we are probably live. Thank you, Tomek, for joining us at DevFix meetings.
My pleasure.
Today we'll be talking about the project Loom, revolution in concurrency or obscure implementation details. So hopefully it will be very beneficial for all of you who join us here at Airmeet. And if you are watching on the YouTube, you can join us at Airmeet. There is much more interactive UI, so you can join us, ask questions, chat, and so on. So if you are watching on YouTube, you can also join us at Airmeet. Okay, and when we're gathering together, the pleasure is that we have a sponsor for this series of meetings. It's Glovo. So probably many of you heard about Glovo. Glovo is the app that delivers food, but not only food, also groceries and other anything that you can fit in the courier backpack. And if you are from Poland, they have office in the Warsaw with more probably than 70 engineers, so worth checking out. And right now I will play short video about the Glovo, and we'll start the discussion. And the plan for today is that Tomek will start with a short 60-minute or less talk, but you are very welcome to interact during the talk. So if you have any questions or so, you can ask them in the Q&A section, or also you can join Tomek live on stage and discuss face-to-face with him if you are brave enough. So.
Oh, come on. So I don't mind being interrupted. So at any moment in time, feel free to pop in with your questions.
Sure. Okay, so let's watch what Glovo is, and we'll start the talk.
Wow, this is the job I've been looking for.
There are no 2 days that are the same. Like, I'm always doing different things. Even though, we have job descriptions, there are always things that come up.
Glovo is growing so much, forces you to be on your toes always, to adapt very quickly, to change.
For me, it's important to work in a company that is really promoting and pushing sustainable and social impact projects.
It's been really amazing. Everybody, all my colleagues have been really helpful, getting me onboarded from the time I arrived. So yeah, I just love it here.
The people in Glovo are amazing. I can definitely feel that people really care about each other, but also like the company, and also the customers and riders and partners who are actually the inside of our ecosystem.
What I like the most about working here is that I have a voice, and I've been growing and learning since day one.
It's been amazing. I'm challenged every single day. I get to work with different cultures, with different people. I get to travel, which is amazing.
At Glovo, we welcome top performers from diverse backgrounds that bring in new ideas and perspectives.
Glovo will be the job of your life because you'll grow, have an impact, and work in a dynamic environment.
All right. I believe the stage is mine, Krzysiek.
Yes, you can go on.
All right. So good afternoon, everyone. And so what we're going to do today is that I would like to talk a little bit about Project Loom. So this is a project that's growing inside, that's baking or brewing inside the Java community. And hopefully it will arrive one day, finally, into the Java ecosystem. So to sum it up, or to wrap it up in just a few words, Project Loom is essentially a way of starting millions of threads. And if you have any experience with Java, you know that creating more than like 100 or maybe 1,000 threads in Java is not a good idea because they consume a lot of resources. The context switching has a lot of overhead. So essentially your application is not doing anything rather than just switching between threads. So typically you don't create more than a few hundreds. With Project Loom, you can create literally millions of threads. And this is kind of like a hello world. Also, you can block and you can sleep everywhere you want. So this is kind of the opposite of what you would normally do with, let's say, reactive programming. So this is a pretty much the opposite approach to what we are currently experiencing with reactive programming, Reactor, Akka, and all this stuff. But by the end of the day, does Project Loom really bring anything to the table, or will it just be this obscure implementation detail hidden somewhere inside the JVM? Do we really care about it? Will it change anything in our daily workflow? So before I start, let's just briefly explain what actually is a thread in Java. Because that's kind of the basics in order to understand why Loom is so revolutionary, or maybe it isn't. So in Java, you basically create threads by calling new thread, and then you're starting them. So a thread on its own is just an object, but when you start a thread, you are actually creating a new, it's called thread of execution, but that's kind of a recursive definition. You are creating a block of code that's going to be executed in background. So preferably on a different CPU, on a different core, or at least it will share the same core with other threads. So you can run, at least in principle, you can run multiple blocks of code at the same time. And this is called the user thread. So you create user threads inside Java, and Java takes care of running multiple threads at the same time. You start a thread, and when you join a thread, you're essentially waiting for that thread to complete. So the join method blocks until code, in our case, system out println, completes. So that's kind of the basics. So this is called a user thread. On the other hand, you have kernel threads. And kernel threads are actually a pretty different beast. So kernel threads are managed entirely by the operating system. So I will stick to Linux because that's what we typically run our applications on. So in case of kernel threads, they are entirely managed by the operating system. And actually, it's the threads, not processes, that are managed by the Linux operating system. So technically, scheduling doesn't happen on the process level. It happens on the thread level. So user threads and kernel threads are not exactly the same thing. So user threads are created by the JVM, and kernel threads are created, surprise, by the kernel. So these are two different aspects. And historically, they were quite different and quite disparate. So historically, I'm talking about Java 1, so in the 90s, we had the concept of a so-called green threads, or more precisely, the many-to-one model. The many-to-one model basically means that the Java virtual machine was starting multiple user threads, but all user threads were sharing the same kernel thread. In other words, JVM, from the operating system's perspective, was single-threaded. It was only running on a single thread, and all threads within the JVM, all the user threads, were actually competing over the same kernel thread. And this was actually fine because we didn't have so many multi-core, multi-CPU servers these days. I'm talking about 90s, or especially the user machines. So that was like okay-ish by that time, but still, that's one of the reasons why Java earns this this story of being a slow language. So that was the very old system and the old way of managing threads. And actually all the scheduling, and by scheduling I mean deciding which thread currently uses the CPU, all of this was hidden inside the JVM. So from the operating system perspective, it was a single-threaded process, but the scheduling, so deciding which thread runs at the moment, was done by the JVM. And this was a pity because operating system on its own already has all the capabilities of scheduling threads, because essentially that's one of the core fundamental things that the operating system does. It's scheduling threads, so deciding which process and which thread runs at the moment. So that was pretty weird to have a JVM doing the same work essentially twice. So there was also a many-to-many model, very uncommon, where there was like a bunch of kernel threads and a much larger number of user threads running inside the JVM. However, very quickly, the JVM switched to a one-to-one model. And in the one-to-one model, a user thread is a kernel thread. And this is the case since Java, I'm not sure, 1.1 or something like that. So quite some time ago already. This move was, the JVM made this move. And from now on, from that point in time, every time you create a user thread, you are actually creating a kernel thread. And to make it even more obvious, you can use a command line tool that comes with JDK called Jstack. And Jstack prints stack traces of every single thread running in your JVM. And if you look closely, these aren't typically the things that we're looking at, but if you look closely, there is a thread ID and native ID. I believe the native ID is actually the exact same number that you will see when you run the built-in Linux utility called top. And top with -H displays not processes, because typically we use top to display to show the list of running active processes. But with -H switch, we are switching into the thread mode. And in that mode, if you look closely at the output at the bottom, there are two Java, well, you might think that these are two processes, but actually this is the same process. We are just seeing two threads. So the PID is not actually a process ID, it's a thread. It's a thread ID. So you can correlate user thread IDs, so IDs of the user threads, with the IDs you will find in the Linux operating system. You can actually, for example, use top to figure out which thread in your JVM consumes your CPU, because the integration is quite tight. All right, so if Linux threads are kernel threads, let's get a little bit deeper. So in Linux, user threads and Linux and kernel threads. So in Linux, Linux threads are actually almost exactly the same as Linux processes. We are taught that a process is a collection of threads that share the same address space and so on and so forth. To be honest, there is not much difference between creating a process in Linux and creating a thread. It's just a single flag that says whether the address space is the same or not. However, from the operating system's perspective, there are no threads or processes, there are tasks. And some tasks are sharing the same memory and some are not. But from the performance perspective, starting 100 processes and starting 100 threads is, well, not quite the same thing, but it's kind of comparable. It's not a totally different beast. So it's not such a hierarchical structure. So as you can see, when you're starting a Java thread, what you actually do is starting a kernel thread, which means you're creating a resource that's kind of comparable to a process, to be honest. And more importantly, when you're creating a new thread, you are consuming one extra megabyte of memory outside of heap. So if you're using, like, let's say 2 gigabytes of heap, every single thread adds a little bit more of memory into that. That's not entirely true, because you are like using virtual memory rather than the physical one. But anyways, it does. It is significant. And also, since you're creating a kernel resource, you are consuming, for example, file descriptors, and most importantly, you pay the price of context switching. So context switching is this process where an operating system decides to temporarily suspend your kernel thread and run or start running another kernel thread, because the number of kernel threads running at any given moment in time is significantly higher than the number of physical cores or physical CPUs you have at your disposal. So the operating system has to constantly juggle your threads just to make sure that all of them get their fair share of resources. So anyways, so this brings us to Project Loom, which, by the way, is still in progress. So all what you see here is not part of JDK at the moment. You can download JDK with Project Loom, but it's not yet in any way embedded into your JVM, so it cannot be like enabled with some switch. But you can already experiment with it. So what's a Project Loom? So technically, it brings 2, maybe 3 abstractions that actually support, as the title says, support creating millions of threads. So you have a concept of virtual thread, a carrier thread, and a continuation. So a virtual thread, something which is entirely new. A virtual thread is essentially like a very lightweight, cheap user thread. And technically, you can create, or even practically, you can create millions of virtual threads. The cost of a single virtual thread is very, I wouldn't say insignificant, but it's much, much lower by a few orders of magnitude than creating a physical thread. On top of that, you have carrier threads. So carrier threads are actually the real kernel threads that are running your virtual threads. So as you can already guess, you have kernel threads, and you can have just a few of them, let's say 4 or 8. But the carrier threads are constantly switching back and forth, running different virtual threads. So it's absolutely fine to run, let's say, 1 million virtual threads on top of 4, maybe 8 kernel threads or carrier threads. And the carrier threads are just constantly stopping or suspending and resuming different virtual threads. And since this process happens inside the JVM, and there are a few extra mechanisms like continuations, more on that in a second, switching between virtual threads, so the cost of context switching is actually much lower than switching physical threads. And this observation can also be seen, for example, in Node.js, where you have only one carrier thread, a single kernel thread, and everything happens kind of asynchronously, because that's the point of virtual threads. And by the way, Project Loom won't make your server suddenly be like 1,000 times faster just because you can create so many threads. It only means that you can create virtual threads. You can create millions of them. But if most of them aren't doing anything or are doing very little in terms of CPU, so for example, waiting for I/O, blocking, being blocked on a lock object, so mutex, countdown latch, whatever, or semaphore, if most of your threads aren't really doing much, then obviously you don't pay the price, or you pay very little price for them, and you only need a handful of carrier threads to support all your traffic. And this is also what we see with reactive programming, but using an entirely different programming model. All right, so the last abstraction that we have to understand is a continuation. So a continuation actually has, we can say it has nothing to do with threads, because essentially it's a piece of code that can be suspended or paused at any moment, and then it can be resumed. But this resuming of a continuation means it starts the execution from the point it was suspended, including all the context, so local variables, loops, all the call stack, and so on and so forth. But suspending a continuation is a very cheap operation that happens inside the JVM. It doesn't go to the operating system. All right, so moving on. How do you create a virtual thread? Just a sneak peek into the API. It's not really that important. You essentially say thread.start virtual thread, and that's it. So the API is very, very, very similar. Notice that the virtual thread is a thread. So you can treat virtual threads just as if they were normal threads in your JVM. So you can treat them the same way. You can create them using Builder API, whatever. This is not like especially interesting. What is a little bit more interesting is that you can create an executor service that creates virtual threads. So if you have some knowledge of Java, you know that executor service was created especially for pooling threads. So in order to avoid the cost of creating threads, you have a pool of threads and you use them just for a short period of time, and then they go back to the pool. So you can have a small number of threads in a thread pool, and you can reuse them. A virtual thread executor is very special because it creates a new thread every time you submit a task to it. So one might say that it defeats the purpose of having an executor service, and that's kind of okay if you use the so-called platform threads. So platform threads are what we have right now, so the ordinary kernel threads. However, if you have virtual threads, it's absolutely fine to create a new virtual thread for each task you submit to an executor service. The only reason to have a thread pool that's backed by virtual threads that are created on demand is that you want to bridge some old existing API and want to take advantage of Project Loom. For example, if you want to take, I don't know, an existing servlet container and you want to replace their thread pool, which is limited, with unlimited virtual thread executor. This theoretically is just a single line of code change. Okay, so what is a virtual thread? And during this presentation, I'd like to dive a little bit deeper into the implementation so that you understand what happens underneath, and you know that there's no magic and then there's no free lunch, essentially. So virtual thread is a continuation plus a scheduler. So you don't know both of these terms, or I briefly mentioned what's a continuation. So a continuation, which is this piece of code that can be suspended at any moment in time, and a scheduler, which is a thread that carries or runs the continuation. So a scheduler is more or less a way of, a scheduler is pretty much just a pool of carrier threads. So how does it work? Let me show you an example of a continuation. So this is basically a piece of code a sequential, normal, single-threaded piece of code that can be suspended, or that can suspend itself at any moment in time. And then we can just like unsuspend it or resume it or unfreeze it, whatever you want to call it. And this is implemented inside the JVM, so this is native code, but it's available as a programming construct. It's not yet known, or not to the point I know, whether continuation API will be visible publicly, or will it just be an implementation detail. But anyway, it's important to understand it because continuations actually appear in multiple different languages. So here's a pseudocode. It's not how it looks in real life, but just to give you a quick overview. First of all, here's a very simple program where we have a main function that calls foo, and then which in turn calls bar. So I'm wrapping the invocation to foo inside a continuation. This on its own doesn't run the foo function. It's just a wrapper around a lambda expression. So what happens next? I immediately proceed to the next line. What happens next is that when I say continuation.run, what will happen is that I actually will run the lambda expression. So I go to the foo function. It just proceeds line by line, just as a normal Java code. So it goes to line 9, it goes to line 10. Line 10 invokes the method bar. I hope you can see the highlight in the source code. So now I am in a function bar. So from main, I jumped into foo, then I jumped into bar. And look what happens. The continuation calls yield. So a yield function auto-suspends the continuation. So the continuation essentially says, I would like to be suspended right now. I want to like go to sleep for a while. So what happens? At this point, immediately, the control flow goes back to line 4. And line 4 is nothing more than or less than just that next line after continuation run. So from the outside world, it seems as if the continuation completed or terminated. However, if I invoke run method again, you would expect that I would go to foo function because that's what the continuation wraps. However, what happens in practice is that I'm jumping directly to line 17. So the whole stack trace, every single argument, every local variable is saved. So we get back the state of that continuation, and we jump immediately into buzz function that may run something else. So as you can see, this allows us to stop the code at any point in time and then move on from the place we stopped. Notice that there is nothing wrong with, let me just quickly go back. There's nothing wrong with running a continuation from different threads. So you can the first invocation to run in line 3 may appear from one thread, and then another invocation to run may appear on another thread. So in other words, we can continue running on a different carrier thread, because this is the point of a continuation, that the first part of the continuation runs on one thread, and the second part of the continuation may run on a different carrier thread. It doesn't have to, but that's the idea. And in between, so between line 3rd and 5th, something else may happen. Some other code may run, which may use a carrier thread. And this is the basic principle. This is how we get all this scalability of creating millions of threads, because every thread is internally backed by a continuation that can be suspended. So let me give you a concrete example. And by the way, you may find continuations in many other languages under different names and with slightly different underlying concepts. But think about coroutines or goroutines in Kotlin and Go respectively. Async await in JavaScript is also a form of a continuation. Generators in Python or fibers in Ruby, all of these are more or less the same or similar concept. Okay, so how does it look in practice? Let's see. So we have a method called sleep on a thread, right? We use it quite often. So if you want to don't do anything for 10 seconds, you call thread.sleep. And in new JDK, the actual implementation is as follows. It's simplified for clarity, but that's the idea. So if what I'm running currently is a virtual thread, I'm going into this special condition. So if it's not a virtual thread, if it's a platform thread, I jump into sleep 0, which is just a native operation. So it goes to the operating system and it tells Linux operating system, please suspend my thread. However, if we are running inside a virtual thread, then sleeping is actually a totally different beast. So sleeping, when you are a virtual thread, works as follows. It says continuation.yield, and you should be already familiar with that concept. Basically, my thread says, I would like to be suspended, because the user, the client of this thread, requested sleeping. So a virtual thread simply says, you know what, I now want to be put in this cryogenic chamber, and I would like to be woken up sometime in the future. So when? Well, here's the line. So before we yield, before we suspend ourselves, we are scheduling the unpark process. So unparking is essentially resuming. So I'm not showing you this code, but you can probably guess that it essentially it just schedules in the future that this thread should be woken up, and that's it. So we have a continuation. So our current thread is a continuation, and we are simply stopping right there. All right, and that's it. So in the same manner, every single API that potentially blocks in Java can be re-implemented, and most of the API is already re-implemented. So for example, well, sleeping is quite simple, but everything related to blocking collections or locks, so semaphores, countdown latches, but also blocking queues, also everything that's related to synchronization, all of these are already like Loom aware, so to speak. So rather than blocking a native thread, blocking the carrier thread, they are just stopping the continuation. And even more importantly, all I/O operations, especially the network operations, are also Loom aware. So for example, if you say socket.getInputStream and then you say read, which is an operation that blocks, underneath it won't block the carrier thread, it will only block the virtual thread. And in that moment, since that moment in time, hundreds of thousands of other virtual threads can use the same carrier thread. So if you know some libraries that work on the JVM, for example, Akka, or maybe some reactive libraries, you will notice that it is more or less similar to all of these. So we are reusing a small number of physical threads to handle a lot of work. It's just that since Project Loom is implemented directly in the JVM, you can expect an insane simplicity, because now you simply create a new thread rather than playing around and fiddling with thread loops or some weird callbacks or flat maps or whatever you want. So this seems really, really promising. Okay, so here's a hello world with...
Tomek, we have a question.
Yes,
yeah, I'm not sure if you can see it.
I can see it. What if I launch run, but it is not sleeping? Will it restart from the beginning, or is it a no up? So the question is, let me think. I don't know. To be honest, how the continuation API works, but to be honest, I'm not even sure whether the API will be visible to the outside world, so to speak, whether it's going to be public. So this is all like implementation specific, and if it's never going to be released to the public, then I guess it's the JDK's JDK's problem to make sure it's used correctly. But that's a fair point. I'm not sure what's going to happen. I'd assume it's going to fail, but it's just my guess.
Okay.
No more questions?
One more question. Yeah. If we can. Not this button. If you compare to coroutine, is it possible to pass values between continuations?
So a continuation is a low-level concept. We should rather talk about virtual threads. So I'll flip that question and ask, can you exchange values between virtual threads? Because that's the apples to apples comparison, I would say. And all the usual mechanisms for exchanging data between threads still apply. So shared memory, queues, and so on and so forth. Because after all, your continuation has to run on some thread. And if you want to pass values between continuations, it essentially means you have two continuations running concurrently and you want to exchange data between them. So yes, either shared memory or preferably passing messages using queues. And I know in Go you have what is it called? Channels, I'm not a Go programmer. And I'd say I hope no one's gonna be sad about it. So I think these are just like glorified queues. So you can do the same thing with JVM. But you are actually touching something really, really interesting here about how to what is the programming model with Project Loom. But I'll get to that in a second.
Thank you.
All right. So this is the hello world, as I already mentioned. So it's, as you can see in line 3, it starts a virtual thread, and the only thing that virtual thread does is it sleeps. And I also put some synchronization mechanism to make sure that I wait for all threads to complete. And just to be clear, and this is not some smoke and mirrors, just to be clear, this you can easily run this code on your normal laptop, and it will work just fine, no matter what you put inside a count variable. So I tested it with 1 million, 2 million, 5 million threads, and it was working just fine, because to be honest, what we are actually doing here is we are creating, let's say, 1 million tasks, so callables, runnables, whatever you want to call it, and we are scheduling to run them in the future. So you could easily rewrite this code by simply creating a scheduled executor service with a really, really long queue, and then just submitting 1 million tasks into that scheduled executor service, which in that case doesn't really sound that exciting, but that's essentially what Project Loom does. However, since we have a much easier and much more, and I would say less convoluted or less tedious API, because we simply create a thread, this makes the programming model a little bit easier, because we don't have this extra abstraction of a scheduled executor service or whatever scheduling mechanism you use. You simply create a thread. So why is it possible? Just to answer this question one more time, what happens here is that we essentially create 1 million, or whatever the count variable is. I parameterized it so that you can play with it. So let's say count is 1 million. We create 1 million continuations, but this 1 million continuations, after almost immediately when they are started, they are yielding, so they are freezing themselves. So at this point in time, a continuation is just a tiny object that lives on heap. It's not this extra stack space, it's heap. So we have 1 million objects on heap, which is really not that much. And let's say 1, 2, 4, 8 carrier threads. And for the first 1 second, these carrier threads aren't really doing anything. And then they are sequentially running the rest of the continuation code. And the rest of the continuation code is just this tiny line called latch.countdown. And I run this code, and with 1 million threads, it actually competes in like 1.5, maybe 2 seconds. So the overhead is actually pretty small. And obviously, this is pretty much impossible with platform threads. So try creating 1 million threads. This means allocating 1 terabyte of memory? 1 megabyte, 1 gigabyte, 1 terabyte of memory, at least 1 terabyte of virtual memory, and the context switching will kill your application almost immediately, or you will run out of memory probably first. So this is something that used to be impossible, and now it's, as you can see, the hello world example. And by the way, if you start to use Loom with less trivial examples, you will notice that it's not so great after all, but I'll get to that in a second. Alrighty, so what is a carrier thread? So by default, a carrier thread is just a fork join pool, common pool. And this is, this is a very small thread pool. By default, it has as many threads, as many CPUs you have. And this is totally fine, because after all, in order to run code, you do need a CPU. So virtual threads aren't somehow magically scaling your server somehow. You are just more efficiently using the resources you already have. Because most of the time, at least when you're doing Java development, your bottleneck will be memory, not a CPU, unless you have a ton of garbage collection. And I'll get to that in a second as well. So unless you have a ton of garbage collection running, your bottleneck will most likely be the amount of memory you can use. And with virtual threads, you are using actually not so much memory, but you do use your CPU very, very efficiently. And that means your overall server utilization is much better. But just in case you want to fine tune how Project Loom works, it's absolutely fine to create a virtual thread using a different scheduler, so using a different thread pool for running your virtual threads. So in this case, I'm just creating a thread pool with one carrier thread, so a fixed thread pool with just one thread. It should have been a fork join pool, but anyways. And believe it or not, with just a single thread, it's still possible to create millions of virtual threads. They would just be competing for a single core, and that's absolutely fine because virtual threads are using CPU only when they have to, and they are not consuming so much memory. So you have overall you have a very good CPU and memory utilization. There's also this new concept that's actually rather independent from Project Loom. It's called structured concurrency. I'm not going to be explaining it very thoroughly because the API is still kind of in flux. But the basic idea is that if you create an executor service within a try with resources block, then when you exit the try with resources block, so when you reach the last line, it will wait for all threads created within that executor service to complete. So in other words, you get this really simple way of doing a fork join type of operations. So you run hundreds of operations or millions of operations within the try block. And then at the moment that when you're done, you're reaching the end of the try block, and your code simply waits for all these operations to complete. I'll show you an example in just a few slides how it can be utilized. But as I mentioned, the API is not finalized and it's kind of an independent thing. However, the creators of Project Loom figured out that since you can create so many threads and they are just like a throwaway threads, they don't want these threads to kind of flow around and leak. So that's why they are bringing some more structured concept into this API. So the whole point of Project Loom can be summarized by this great quote by Kay Horstman in his talk about concurrency. So essentially he says that we now have tasks, not threads. And this is a great quote because for years we were taught to use thread pools and to fine-tune thread pools and to watch out for thread pools. This was just this extra level of abstraction. So when you're creating an HTTP server or when you are building, I don't know, an online game or whatever, we are always thinking about the limited number of physical threads or kernel threads that must handle much larger traffic. That was the whole point of creating frameworks like Akka, where you have a tiny number of threads running millions of actors. So in some sense, a virtual thread is something like an actor, or to be more to make a better comparison, it's very, very easy to implement Akka using virtual threads because you simply create a virtual thread for each actor, so to speak. So for many years, we were taught how to somehow overcome this complexity of mapping a limited number of kernel threads into a much larger number of tasks that we would like to handle. These days, or actually when Loom comes out, theoretically, we may no longer need thread pools because we could just create threads like crazy. So let's say, and this is a very, very stupid example if not using virtual threads, let's say we want to run some code after 8 hours. What we can do? Well, just start a virtual thread that sleeps for 8 hours. And this is actually fine with virtual threads. Because a virtual thread on its own doesn't consume a lot of resources. So there's nothing wrong with having a virtual thread hanging somewhere for 8 hours and then just doing something. This is totally fine. Without virtual threads, we would have to use scheduled executor service or some scheduling mechanisms inside our frameworks or maybe some libraries or whatever. In this case, all we have to do is just like create as many virtual threads as we want. Of course, memory is not infinite, but anyways, it's much larger than we need. So what else? Another example. Let's say you're building some massive multiplayer game or a chat service that handles millions of users, or you want to handle thousands of connections that are, or hundreds of thousands of connections that are established with your server. So what you can do, you simply create an executor service that uses virtual threads, which you see in the first line. And then every time a new player appears, or I don't know, a new connection, a new message, whatever, you simply, well, submit into a thread pool. But what actually happens underneath is you create a new thread pool for each, a new thread for each message player, connection, whatever you want. And this is totally fine with virtual threads, and it makes our lives so much easier. There is no more tuning. There is no more making sure that you have enough space in your thread pool. There is no more monitoring and so on and so forth. You simply throw away as many threads as you want. So that's why this mantra, tasks, not threads, is so useful. So what else? This is an example of structured concurrency, by the way. So let's say I want to download 10,000 images. So I already have a method that downloads a single image, and it uses, I don't know, REST template, or it uses HTTP client. I mean, any client that's essentially blocking. But what I do is I create an executor service that's backed by virtual threads, and I simply iterate over all images. And by the time I reach the last line of the try with resources block, the last line simply waits for all download operations to complete. And that's it. So if we wanted to do the same thing with ordinary threads, that would of course be possible. But what we would have to do is create a thread pool, of course, much smaller thread pool with platform threads, like 100 threads, for example, and then a very, very long queue that would accommodate 10,000 tasks. But that would also mean that we do not have that great concurrency, because we have, let's say, 100 download tasks running at any given moment, and the remaining 10,000 minus 100 are waiting in a queue. With virtual threads, we have 10,000 concurrent download operations, just like that. And since all of these operations are essentially like doing nothing because they are waiting for the network, this has no impact on performance, but it's much faster. Okay, but there's one problem, because at the moment there's nothing preventing us from downloading not 10,000 but maybe 10 million images, which means we may start an unsurmountable number of connections, and we will fail, but we will just fail in some different place. And this means, surprise, that we have to relearn all these weird synchronization mechanisms, like countdown latch, which waits for a few tasks to complete. Because when you have threads, you somehow have to coordinate these threads. It's not like you can simply create a thread and then just forget about it. You only live once. You do have to take the results of that thread somehow. You have to compose the results of these threads. So you have to wait for them. Countdown latch is Loom aware, so it's absolutely fine to wait on a countdown latch. However, you do have to use it. And that's kind of a class that I haven't used since 10 years or so. And the same applies to a semaphore. I think it's the first time I used semaphore since the days I was at the university or something. And now it's exciting again, or we have to use it again, because how would you implement throttling? And by throttling, I mean do not run more than a given number of tasks at the same time. Previously, throttling was kind of happening naturally because you had a thread pool. And when you have a thread pool with 100 threads, there is no way on earth more than 100 tasks will run at the same time. Now you have a thread pool that's virtually unlimited, so you can, or theoretically unlimited. So you have to put the limit yourself somehow. You have to do semaphore, try, acquire, and all this weird stuff. That being said, what are the problems and what are the limitations of Project Loom? So first of all, when you have an application with very deep stack, and I'm looking at you, Spring, and I'm looking at you, Reactor, and I'm looking at you, every single framework that we have these days in Java, you will have very deep call stacks. And a continuation is cheap. However, the deeper the stack, the more memory continuation will consume on heap. Because when you are suspending a continuation, you have to take the whole stack of the continuation, compress it mildly, and put it on heap. And if your continuations are very shallow, so all you do in your continuation is just sleeping as a first line, then your continuation is insanely cheap. However, when you're running inside a very sophisticated framework with tons of dependencies and that interleave each other, and this is a stack trace from my blog article from many years ago, which has 200 or 300 lines of code. This means that your continuation will actually consume quite a bit bit of memory. It's not going to be 1 megabyte, which is the pre-allocated amount of memory for each thread, but anyways, you will see a significant memory impact, which also means that virtual threads aren't free lunch, especially when you're running them on a non-trivial workloads. Secondly, there is no preemption. So for those of you who don't know, preemption is the process when a Linux kernel can suspend forcibly a thread that runs for too long. So it's easy when a thread suspends itself because it's sleeping, because it's blocked on I/O, because it's blocked on a semaphore or countdown latch or whatever. That is kind of obvious. However, when your thread simply consumes CPU, so it's doing like number crunching, crypto mining, some hashing, compressing, media, whatever, if your virtual thread simply consumes CPU all the time, then in case of Project Loom, there is currently no way of stopping such a thread. It has to voluntarily say that it would like to be suspended at a given at this moment in time. There is no such problem with platform threads, so kernel threads. When an operating system thinks that a given thread or a given task is running for too long, it will simply preempt that thread and it will continue running. It will continue with another thread. So platform threads, at least at the moment, are fair, which means that they get a fair share of the CPU time. This is not the case, at least at the moment, with Loom virtual threads. So keep that in mind if you want to do some number crunching. And it also means that you cannot start million threads, crypto mining, because it won't give you like 100-fold or 1,000-fold increase in performance. No, because you still have the same CPU, and Project Loom doesn't make your CPU magically work faster. It's just using it in a different way. Also, there is a bunch of unsupported APIs. The list isn't really that long, but there are quite a few operations in the project in JDK that are not Loom aware. Most importantly, system out. So system out println and file API. But the server, so the socket API, server and client API, are already fully supporting the Project Loom. But also keep that in mind. All right, so the last thing is, and I already briefly mentioned that, so platform threads, so kernel threads are using Stack. So this is this area of memory that lives outside of heap, and each thread has a pre-allocated give or take 1 megabyte of memory. In case of continuations, the memory consumed by a continuation that's frozen or suspended is on heap. This means that if you create 1 million continuations, or 1 million virtual threads, you have 1 million objects, possibly long-living objects on your heap, and the garbage collector has to go through all of them. So the pressure on the garbage collector is actually much higher than on a typical application. So this means that you cannot simply replace platform threads with virtual threads and your application would just magically be more scalable. It doesn't really work this way. But the final question, so does it all mean that I no longer need reactive programming and I no longer need all these fancy frameworks and all my new knowledge of Reactor, RxJava, Akka, SmallRye, Mutiny, Akka was already there. Okay, like a Vertex and a ton of other frameworks that looks so shiny on your CV. I no longer need all this knowledge. Well, yes and no. So if you were using reactive programming just to run a few operations concurrently, maybe you will get away with just using Project Loom. So just starting a few virtual threads and you're good to go. However, if you use reactive programming for something a little bit more complex, where you needed some orchestration, some composition of tasks, then most likely you will still need this clumsy API. However, it can take advantage of Project Loom. So in the simplest case, for example, when you're like just downloading some data and you want to make it concurrent. For example, you're using REST template, which is a standard HTTP client you will find in a REST client you will find in Spring applications. As you may have heard, REST template is maybe not deprecated, but its development is somewhat frozen at the moment in favor of web client, which is the new shiny HTTP client that's non-blocking. All right, so it's built on top of very different API. However, with Project Loom, it's absolutely okay to use REST template because it uses blocking API, but the blocking API is Loom aware. So it's absolutely fine to use REST templates to make hundreds of thousands of outgoing requests running concurrently, because all of them will eventually be suspended. So you won't, you can easily use virtual threads, and it will just work. And that's kind of exciting, because you can take your old application and you no longer have to rewrite it to reactive programming. So you no longer have to use these fluxes and monos and all this creepy stuff. What you can simply do is just replace a thread pool with a virtual thread pool, and you're off. All right, so your application is magically scalable. I'm kind of joking here because there are quite a few traps, which I already mentioned. So like throttling, like preemption, like stack versus heap utilization, and so on and so forth. So definitely Project Loom is not a silver bullet, but it's something that may help you in some scenarios. So the Project Loom actually addresses asynchronous programming. It doesn't really address parallel programming, because parallel programming means you have multiple threads and your code runs essentially at the same time. So there's nothing new in that regard. You still have a limited number of CPUs. However, with Project Loom, you can very, very easily do asynchronous programming by simply starting more and more virtual threads. So that's something that is being addressed by reactive programming as well. However, reactive programming also supports quite a few other features like back pressure, so slowing down a producer when the consumer cannot keep up with the load. There's change propagation, so every time something changes upstream, the change is kind of automatically propagated to everyone who needs that value, and that's not addressed by Loom as well. And there's composability. So essentially all these mechanisms and the programming model, which allows you to take multiple asynchronous operations and somehow chain them together, compose them together. The completable future that's available since Java 8 actually addresses some of these concerns. But yet again, the reactive frameworks provide so much better API that I don't think they will go away. However, many of the changes that they introduce, so for example, web clients, so asynchronous HTTP client, asynchronous HTTP servers, and so on and so forth, they will no longer be needed, because we can achieve the exact same thing or a similar thing. More on that in a second. We can achieve a similar thing by just using virtual threads. So we will still need the API. However, the underlying implementation may be greatly simplified. And in some cases, we may get away with using the raw Loom, but just as these days we do not use platform threads, so you don't often see new thread.start in your code, we will probably not use Loom directly, but it will be a blessing for library and framework developers. All right, so I believe I already answered this question. You probably shouldn't. You shouldn't just blindly replace platform thread with virtual threads, because they behave differently. And I don't mean only from the performance perspective, but also memory consumption patterns are different. You do need throttling that was previously handled by a limited thread pool, like by default, and now you don't have it. So you do need a throttling mechanisms on their own. And there are probably tons of other issues that you will discover along the way, like preemption for the time being. All right, so the final question is, because I still hope I got you excited with Project Loom, even though it has some shortcomings. So 2 or even almost 3 years ago, one of the Loom project's developers said that it should very likely land in JDK 17. We are now waiting for JDK 18, and Loom will not be there. So this project is already past it wasn't a deadline, but past the initial estimations. However, the good news is that you can already download JDK 17 and JDK 18 with Project Loom. It's a completely separate installation of Project Loom. If you're using SDK Man, it's already there. And you can play a bit with it. You can take the code that creates 1 million threads and see that it actually works without melting your your computer. Alrighty, so there are already a few Java enhancement proposals. Feel free to read them. They explain what a virtual thread and structured concurrency is in a slightly more abstract level. And I leave you with a bunch of links. So a few other presentations and already a library, Java Async Await, that uses Project Loom as a proof of concept. Also, there are a few blog posts of people who tried Project Loom and their thoughts about it, and also quite a few critical posts regarding Project Loom, especially the last two. Do Loom's claims stack up? These two posts are created by the Jetty team. So the servlet container Jetty, very, very popular. And they tried Project Loom. It was like a year ago, so things may have changed. But they tried Project Loom, and it wasn't really bringing that much to the table. And to be honest, they noticed that you don't really need that many threads to run a servlet container. However, the garbage collection pressure was much, much bigger. So actually, it was kind of a lose-lose situation. But it may change in the future. Okay, so that being said, thank you for listening, and I really, really, really encourage you to give me some questions. The slides are here, nurkiewicz.com/slides/loom, exactly what you see here. So you can you can get some extra materials from there. And yeah, listening to your questions, as Grzesiek mentioned, feel free to pop in with your camera and ask me face to face if you prefer that. And yeah, so
definitely. So we have Zbigniew. He asked 3 questions, and I asked him to join us on stage. So Zbigniew, if you are ready, we can. You need to accept the invitation, and you will show up. Just to give you to make a bit more context about the question itself.
I see that I will enable. I will. Okay.
Zbigniew, I can hear you.
I see my background, but I cannot see myself for some reason.
Different screen, I guess.
No. Okay. Sorry. Sorry for that.
Voices now.
I don't know, because my camera is on. I see the. Maybe. Sorry, guys.
Here you are. Oh, virtual background.
Yeah. Something with that HP laptop. Okay, but I won't work on that. Oh, now you see me. I don't know what actually happened. Okay, I have a question to Tomasz because what I afraid a bit, and what I encounter in my past. Then I must admit that I encountered your article from Tomasz from 2015 about that completable future was breaking Liskov principle, and I actually encountered it. And it was a similar case, maybe to the similar thing, which I would like to ask you in the second question, that what will happen if one of this, because you told about this try with resources clause, and what will happen, and I afraid that this could happen when one of calls will go forever. For example, it sleeps, whatever will stay, and we will remain in that loop, in that try with resources forever. And I think that developers should be aware that something like that could happen. Like in this case, I encountered this with this breaking of Liskov principle, because basically you cannot cancel completable future. Sorry for that convoluted question, but for sure you understand. And your article was great. So I encountered it shortly after I resolved the issue, but it was a real headache. What actually happened? So two cases in one.
All right. So first of all, thanks for reading the article. I actually had to.
Now I cannot hear you for some reason.
Cannot hear me, but Grzesiek, can you hear me?
Yeah, I can hear you, Tomek.
Okay, so I'll just keep talking, and you should speak if you should hear me. I'm here. 1, 2, 3. 1, 2, 3.
Everything is fine, Tomek. So Zbigniew, can you hear us?
Give a second to Zbigniew, because I think he's dying to hear the answer.
Okay.
Can you hear us?
Yes, and I change. I don't know if you can hear me, but I can hear you now.
We can hear you, and okay, great.
Thank you.
So,
sorry for that.
No problem. So first of all, thanks for reading the article. I just Googled it and I found it. So yes, so completable future does break the list of substitution principle because it cannot be cancelled. So even if you cancel a completable future, it doesn't cancel the underlying operation, and that's kind of the leaky abstraction, which means you cannot simply replace completable futures with completable futures. And I guess that's what you encountered.
Yes,
and
yes,
I kind of understand the reasoning, but anyways, not talking about completable futures here. Regarding the difference between thread and a virtual thread, you are without going into the try with resources question, they are different, which means you cannot simply replace one with the other and expect your application to just work. It will compile. It may even work for happy paths, but it won't simply behave the same way. Because of throttling, because of different memory usage patterns, and so on and so forth. Regarding the try with resources, this is essentially, as you can guess, the thread pool now implements auto-closable, which means you can put it inside a try with resources, and inside the close method, what happens is that it waits for all tasks to complete, and that's it. So you can easily implement the same pattern today, with just doing an ordinary try finally and then using shutdown now, I believe, on an Exator service. So because it wasn't previously possible, so you couldn't previously say try and create a thread pool inside try with resources, I don't think you will shoot yourself in the foot here. Because it's not like you can replace an old executor service here with a new one. Because it wasn't possible before, so you cannot simply refactor by accident. But it doesn't mean you won't shoot yourself in the foot in many other places. The especially non-trivial one is the one with preemption. So if your virtual thread is doing a lot of number crunching, and previously used platform threads, so the ordinary kernel threads, it worked just fine. So you could have hundreds of threads doing CPU intensive tasks, and it was just okay. And with Project Loom, you may effectively hang your application, so starve, to be precise, because all the other virtual threads will be starving. They will be waiting for a carrier thread, and the carrier thread will occupy the CPU forever. So technically, you will perform the same work in the same time, but it won't be fair. Because it's your virtual thread has to stop at some point, but it won't be fair, essentially.
Yeah, and I think that this feature has to be underlined with big letters, because it could end badly for someone.
Well, okay. To be honest, I don't think it's by design, or it's just a work in progress. So maybe it's already not like that, but it was like that the last time I checked with the pre-built JDK.
Okay, so thank you for your answers. Thank you.
Thanks.
Yeah, sure. You have also the question about the performance. Was it answered?
Yeah, sorry, I forgot about that. So another question, maybe there is a comparison between how, because you mentioned that with the containers, with a Jetty container. However, is there any real performance comparison between what could be achieved with the traditional approach and this new approach?
So I believe the benchmarks are very premature at the moment, because it's still work in progress. It's very heavily work in progress. And also quite a few times I crashed the JVM. I mean crashed as in segmentation fault, something that I wouldn't normally see with JDK ever. And in case of Loom, it actually crashed very, very abruptly when I was doing some performance benchmarks. So at this point in time, I wouldn't really measure the performance, because it's still cooking. However, regarding the Jetty team, what they found out is that the number of threads wasn't really their bottleneck. But on the other hand, they realized that the garbage collection was doing so much more work, because it had to go through all the continuations that were suspended. So that's one thing. However, I can already think there are some micro benchmarks done. The simplest use case, the hello world, which is not very representative, but anyway. So in the simplest case, when you're creating millions of virtual threads that are just sleeping and then waking up, if you compare that to standard code that would use a scheduled executor service, chances are it will actually be faster. The project Loom will be faster because there are less context switches, because all the carrier thread does, and there are just a few carrier threads, all the carrier thread does, it just goes through loop in a single loop, and it just runs continuations one after another. So in that case, it may be faster, but your mileage may vary, and we should definitely wait for the JDK with an official Loom implementation, maybe +1 or +2, because they will need a little bit of time to polish it.
No context switches. Okay, so thank you again. Thank you, guys.
Thank you. Thank you. Great questions.
Okay, we have 3 more questions.
Keep on
First
coming.
one is from Honza about the context switching. Can you explain it again? Because there's a question that there is still like misunderstanding between.
Yeah. So when you have 2 threads, let's simplify it greatly. So you have just a single core, a single CPU, and you have 2 threads. And both of these threads are like using a CPU or blocking or sleeping, whatever. It doesn't really matter. What the operating system has to do is it has to take the snapshot of a thread, and it happens on the OS level. It has to take the snapshot of the thread, put it in some kind of special place in memory, and then move the context of another thread that was suspended back into the CPU. So this happens on the operating system level. So it actually takes a few hundred microseconds. I don't have exact numbers, but it is actually a significant amount of time to move one thread from out of the CPU and then move another thread back to CPU. So that's what happens with platform threads. If you have virtual threads, you have only one carrier thread, so there's only one kernel thread. So kernel thread, carrier thread, you have only one of them. So from the operating system perspective, there's no context switching. So you don't have to go to the operating system to switch between threads. So that's a big win. However, you do have to perform this kind of micro switch because you have to switch between virtual threads. However, this operation happens inside JVM. And also, it happens only with the continuation. So it's implemented inside a continuation, and all it does is it takes a continuations stack, it puts it into an object, which is like stack fragment something, I don't remember the name of it, and then it takes another, and then it simply runs the next continuation. So from the operating system's perspective, you have a single kernel thread or single carrier thread that run one continuation. That continuation stopped because it was suspended, and then it is running another continuation kind of in a loop. So in some sense, this is similar to an event loop design pattern where you have a single thread that handles multiple sockets or multiple connections at the same time without switching between. I hope this clears a little bit, Hansa. Feel free to jump in with a microphone if you want.
Yeah, if you want, just raise a hand and we will join you on stage. But I think it was very clear explained. And let's see what we have more from Dariusz. Question from Dariusz. Is there any special support for the GC operation on heap for managing continuations?
I don't think so. So from the garbage collection perspective, the continuation that's suspended is no different than any other object. So it will eventually land in the old generation, and you will pay the cost of like doing some garbage collection here. Of course, when a continuation runs, so when it is pinned to a carrier thread, it's not a subject to garbage collection because it actually runs on stack in that case. However, when it's wiped out from the stack, it's placed on heap, then it's treated as any other object. And also, obviously, when a virtual thread completes, so when you finally reach the state where the start method completes of a virtual thread, this object is now eligible for garbage collection, and it will be taken out of your memory. But as long as virtual thread or a continuation is suspended, it's still runnable, so it still has to live on heap. There's no such thing as like, I don't know, special area of memory for continuations or whatever, simply because the generational hypothesis So as a recap, it's this hypothesis that is used by many garbage collectors that some objects are very short-lived and some objects are very long-lived, and there is pretty much nothing in between. So in that case, in case of virtual threads or continuations, this hypothesis still applies. So you will have virtual threads that are very short-lived, and they will never leave the young generation. And there are some virtual threads that will live like forever, or they will live for a long time. Like in my silly example where you were sleeping for 8 hours, this is definitely a continuation that will land in the old generation very, very quickly.
Definitely. And last question from Miłosz. Does thread priority apply to virtual threads as well?
I will flip that question. So does thread.priority apply to platform threads? And the answer is no. It is not used neither by virtual threads nor by platform threads. It's more or less ignored. I even believe, I'm not sure whether priority is ignored or if it fails at runtime on virtual thread, but it makes no difference.
Okay. This one's answered by Mark. Okay, this is the last one from Honza again.
No, so the bytecode, it's bytecode compatible. Of course, you will see changes, like you're not starting a virtual thread, you're not starting a platform thread, you're starting a virtual thread. So it's a different method call. But the bytecode itself is that there are no changes in bytecode. However, there are significant changes in the JVM itself. So like the project Loom is mostly written in C or C++ or whatever JVM uses. So most of the work is actually done and in the internals of the virtual machine, and there are some API changes. So there are some extra API needed to support virtual threads. However, bytecode remains the same. So you can take your code written in Java 1 and it can still take advantage of virtual threads if you like recompile it. Yeah.
Definitely. And all questions are answered. So guys, if you have any other more questions, you have the last 10 seconds to shoot one or raise your hand, and you will be able to join us on stage and discuss with Tomek as Zbigniew did. But if there is no more questions, Tomek, thank you very much for sharing your knowledge. Very deep conversation and a very deep presentation. So thank you very much.
And thanks all of you for staying so late, and I hope you learned something new, and I hope you enjoyed the talk and you will experiment with Project Loom.
Very soon, whenever it's ready. Thank you.
It's ready when it's ready. Thanks so much.
Yep. Bye-bye, guys.
Bye.